given a statistic. Let's talk a little bit about sampling frames. So sampling frames, recall, are that second step in the process. So what is a sampling frame? Well, it's a list of all the units in the population. All right, I already said that a sampling frame bias occurs whenever the frame that you have doesn't match the population. So I've drawn a little picture that will make this really clear. So let's go back to the fundamental question of statistics. So the fundamental question of statistics is I've got a population. So this box is meant to represent that population. Now, recall that there's something I want to know about that population. That something is the parameter. Say it's the mean, whatever. All right, so I want to know the mean of all the people in this box. Okay, well, I can't go do a census. Instead, I'm going to do a sample. I'll draw a sample from this, and from that sample, I'll get a statistic that is meant to infer the parameter. Okay, so now let's say I have a sampling frame that's represented by this box. Now, notice that my sampling frame does not match the population exactly. So let's talk about some of the areas. Start out with down here. So there may be a lot of names on my list that are not in the population. For the sake of argument, let's say I'm marketing a consumer packaged good to women ages 25 through 40. I get some list, and that list is not just women ages 25 through 40, it also has women who are 60. It also includes the names of men. So I call somebody up, and it turns out it's a guy. First thing that I want to do is eliminate that guy with a screening question. So I would ask, what is your gender? And if the response comes back, I am a male, then we terminate the questionnaire and move on. They say, thank you very much, sir, have a good evening. And then we call the next name. Likewise, if I call it up and one of my screening questions is, what is your age? And the woman says, I am 55 years old, we terminate the call and say, thank you very much, have a nice day. All right, so this region then is very easy to deal with using screening questions. The sampling frame bias is out here. So these are people who are just not on our list. And, you know, if they are systematically different from the people in the list, then that's what we mean by a sampling frame bias. Our statistic is going to be biased. All right, so the sampled population is this region in the box. Now there's two little boxes that we've omitted, and to be honest, I probably should have made these little boxes big boxes because they can also be, they're often quite large. So the first of these boxes is the non-respondent. So there could be a whole lot of names on this list. We call them up and we can never get a hold of them. So in real life, that non-respondent portion is often, you know, 3/4 of your sampled population. So that box should be 3/4 of this population, of the sampled population, because I just can't get a hold of them, or they won't respond. There are other ways that a person will opt out. So sometimes people just simply cannot participate. There's lots of ways that that could happen. So let's go back to my little example where I have women 25 to 40, and let's say I call up a non-native English speaker who happens to be, you know, a U.S. citizen living here, and she's 30 years old, so she's clearly in the population. But my interviewer doesn't speak her language. Okay, well then I can't get data from her, and we've omitted her. If I send out a mail or internet survey, there could be people who can't read, and therefore they can't participate. It's another potential source of bias, although I'm much more worried about the non-respondents in most cases. If I really have issues with language, I better get my interviewers that can speak the other languages that I care about. So address that on the front end. This is the one that's usually much harder to deal with. Now at this point, there is a really nice your turn. And this will be a discussion board question in class. We'll have this discussion in class. So we have a little example. What I want you to do here is identify the population. So what exactly is this outer box? What is the sampling frame described in that little example? Then I want you to think about which groups are omitted because of the sampling frame. So what sorts of people sit out in this region? And then how do these omitted groups, or how might these omitted groups affect the statistics that you're estimating? So let's just kind of think through the biases here. All right, so again, let's have that as a discussion board question. Moving on. There are really two types of samples to a statistician. So a statistician is going to divide samples into probability samples and non-probability samples. And this is a real critical distinction. So probability sample is something that's slightly different than we've talked about so far. So probability samples where every element in the population or every unit in the population has a known non-zero probability of being included in the sample. So up until now, we've talked only about simple random samples. And with a simple random sample, every unit has the same, an equal probability of being included in the sample. Statisticians relax that constraint, and we've develop methods for accommodating non-equal probabilities of being included. So as long as we know what the chance of inclusion is and it's non-zero, then we've got a probability sample. So let's think a little bit about these two terms. So a zero probability means that a person can't be included. So if I've omitted people from my sampling frame out here, every person in this region has zero chance of being included in a sample. All right. If you're not on my sampling frame, there's no way you're going to enter my sample. Okay, likewise, if I did something like a mall intercept, all people who don't go to that mall have zero probability of being included in my sample, and therefore it's no longer a probability sample. Now, if I know the probability, so what might be an instance where I know the probability, but the probabilities aren't the same? This often comes up when I have subpopulations. Okay, so maybe I divide my population into old people and young people, and it's a lot easier to get old people into the sample than young people because they'll actually talk to me on the phone. Well, maybe I oversample old people, so I draw more old people into the sample. I have a smaller sample of young people, but as long as I know how big those two groups are from, say, the U.S. Census, then I can make adjustments using weights. Right? So that's often done with public opinion polls. And sometimes you'll have two news organizations who use exactly the same data, yet come up with slightly different estimates, and it's because they make different assumptions about these weights. That's all right. The other type of sample in this world is a non-probability sample. That's everything else. Now, why do we care about this distinction? So we care about this distinction for the following reason. All of the statistical inference methods that we've talked about so far and we'll talk about in the future, so confidence intervals, margins of error, any sort of hypothesis test, all of these methods of statistical inference assume you've got a probability sample. So the first assumption in Chapter 9, when we talked about confidence intervals, is assume that you've got a random sample of size n from some population. Okay. If that assumption is not made, you're not allowed to use Chapter 9. You're not allowed to use Chapter 10, not allowed to use Chapter 11, 12, 15, 17, and so forth. So that's a big problem. All right, so in practice, there is no perfect. You usually don't get perfect samples, and you kind of fall somewhere on a continuum, and you're gonna have to make a judgment call. So maybe you've got some biases, but you'll still go ahead and use some of the techniques in 9, like computing a confidence interval or margin of error. All right, so in essence, we can quantify the sampling error with margins of error and so forth. Probability samples usually also mean it's going to cost more. So the closer you want to get to a probability sample, the larger the incentive that you're going to have to offer. So you offer an incentive, people are going to be more likely to respond to your survey instead of throwing it out. You may have to pay more to get a better sampling frame. So all of these things imply a higher cost. Okay. With many samples, you have to identify the factors that introduce the biases and take them into consideration when forming your conclusions. So, often you're stuck with the data that you've got. You got to work with what you've got, and you've got to identify what the biases might be and take that into account. That this is probably overestimating something. This is where statistics gets really squishy. Let's talk about bias versus sampling error. So I've drawn a sample from some population. I've computed a statistic. What is that statistic equal to? That statistic is really made up of 3 pieces. So the 3 pieces are as follows. That statistic is really estimating, is really a function of the parameter. So if I want to, I draw a sample of people, and the mean purchase intent, the statistic is 4.5. Well, let's say the true purchase intent was 4. Okay, that's the parameter. Add to that any bias that might be there, and then there's also sampling error. So sampling error refers to the fact that you have a sample rather than a population. Okay, now we've done a lot of work in this course where we've talked about on average you get the truth. So the on average you get the truth is saying that the sampling error is 0. So earlier in Chapter 8 we talked about sampling distributions, and so sometimes the sample that you draw gives you a statistic that's too high, sometimes it's too low, but on the average you get the truth. So so the sampling error has a mean of 0, is just restating that on average you get the truth. Okay, whenever you have a bias of 0, your statistic is said to be unbiased by statisticians. Now, slightly more concrete example of this formula is, we want to estimate a mean. So here's your sample mean. Well, that's just the parameter plus any bias that might exist plus some error. Now, let's go look at an example of when you do have a bias. So if this is the true mean, but there's bias in my sampling procedure or my measurement procedure, I got a biased question, or I've got non-response bias that leads to some problem. What's the effect of this? Well, the effect is that your samples are no longer going to be centered at mu. Instead, they're going to be centered at mu plus b. Okay, so if my leading question leads people to giving me an answer that's systematically high, now what's going to happen is that my sampling distribution is going to be centered at mu plus b. So I'm estimating mu plus b, I'm not estimating mu anymore.